Ask not what neuroscience will do for AI, ask what AI will do for neuroscience. I would say the benefit is still more from machine learning to neuroscience than from neuroscience to machine learning. We're entering this era where making sense of data is no longer possible by looking at it or even running statistical tests. You really have to run machine learning algorithms to detect anomalies in the data, unexpected things, and also to learn patterns from the data.
Because it's such a massive data set, and then also the interconnections and everything. One person can't literally get their head around it, right? You need to use AI.
AI, machine learning is part of AI, and that spans a lot more. It spans multiple, but also combining physical methods, and we overestimate how close it is, the connection between artificial neural networks and the brain. The brain remains a mystery. I think we will learn to live in harmony with artificial intelligence. I'm very optimistic about that.
The human brain produces more data in a day than the world's largest supercomputers. In neuroscience and AI, the biggest bottleneck isn't discovery, it's data. Labs are drowning in massive data sets, yet most researchers still struggle with fragmented, outdated systems. What if there was a way to unify, simplify, and accelerate breakthroughs? Today, we're cracking the brain's data code and discovering how AI and neuroscience collide with Dimitri Yatsenko of DataJoint. Welcome to the show, Dimitri.
Thank you, Chris.
Well, I'm always interested in the brain and gray matter. So why is managing neuroscience data still such a massive challenge today?
This is a multidimensional question.
That's the kind of question I like to ask.
So managing data in general in any space right now is challenging. And we're creating a lot of tools that are meant to make it easier, but because tools proliferate and evolve, just to stay on top of things, it requires constant attention. You cannot, so what a lot of neuroscientists end up doing is figure out something that works, build it once and freeze it and try to use it for many, many years. And then it's become just too fragile. Nobody wants to touch it. And that doesn't serve them. It doesn't serve science because you cannot take advantage of the latest analysis techniques, technologies. So to stay at the cutting edge, so the types of data and the types of analysis that neuroscientists perform is on the same scale as an enterprise. In terms of the complexity, neuroscience data is probably the most multimodal. We have so many modalities.
Well, maybe take a step back and explain a little bit about what neuroscience is. Asking for a friend, of course.
Okay. So neuroscience is really a constellation of sciences that are all focused on. So it can involve physiology, physics. A lot of it is focused on instruments. So developing some of the biggest breakthroughs. If you look at how discoveries have been made in neuroscience, it's very rare that you make a hypothesis, design a test, and then confirm or disconfirm your hypothesis. It's usually you try a new instrument, design a new instrument, look somewhere where no one's looked before, and go, aha, this is something I have not seen. So to define neuroscience, it's a constellation of sciences that are focused on the study of the nervous system, not just the brain, central peripheral nervous system. The general principles. I focus on systems neuroscience, which goes all the way from molecular to cellular to circuits to systems and related to behavior. So related to ethological aspects of us, but most of it is done in animals. So focusing on ethological aspects.
Well, where is the data coming from? It's because it is all about medical and brain and, like you said, molecular.
Yeah. We can do a lot in basic science that we cannot do in clinical science in terms of methods. I will get a little bit more detailed about a particular method that we've been using a lot called calcium imaging using multiphoton microscopy. So that allows us to image deep in the brain. And by deep, I mean a millimeter. Mm-hmm. So that's deep by microscopy standards in an intact brain. In intact circuits, and to interrogate tens of thousands of cells at the same time, to see their activity in real time in a awake behaving animal as it performs various tasks as perception, decision making, memory, those types of things. So we can actually, so just a couple of decades ago, that was considered sci-fi, what we're now doing. And so one project we will probably talk about is microns that studied a full cubic millimeter of the brain, recording from every neuron. So that's where the data comes from, and it's massive. So that's one modality, but as I mentioned, neuroscience is most multimodal. So where we combine recordings. One of the most exciting new developments in neuroscience is, thanks to AI and machine learning, is to be able to analyze behavior that's more naturalistic. And to study all the years prior to that, we've designed more of very rigorous structured protocols for behavior. It was button pushes, and that was very low dimensional. So if you only have low dimensional stimuli, low dimensional behavior, then your analysis is limited by that. So now if you can study the brain in its full behavioral repertoire with machine learning, that opens up. So very surprisingly to me, the biggest changes, the most evolution recently has been from being able to capture behavior. Much more than before. That was more operant behavior. For the past 100 years, it was button pushes.
Capturing behavior of what's going on in the neurons within that very small, like you said, 1 millimeter cubic area, which, for those that don't know metric that much, but I mean, it's less than a 16th of an inch on the side of a cube, something like this, right?
That's right.
So very small. And you said that's a massive amount of data because there's just so many neurons crammed into that very small cube of gray matter.
Yeah.
Right?
So maybe I'll give a little bit of sense of scale. Yeah. So I think one good comparison, I don't remember who came up with this comparison, but the human brain can be compared to a stadium filled with spaghetti and meatballs, basically.
Okay.
So that's roughly the scale. So a meatball is roughly the size if the brain is the stadium, and the pasta would go from really thick pasta to capellini, like really, really thin pasta, different scales of connectivity. So, and neurons themselves take up, the soma take up a small portion, very small portion, less than 1%. And it's all the connectivity, all the gray matter between the cells, that's connectivity. And so it's very, very highly interconnected. In a cubic millimeter, we have about 100,000 neurons, and that is the same. So we study mice. In humans, it's roughly the same. And then there's an enormous amount of supportive cells that are more, astrocytes and cells that support the function of neurons.
What are some of the biggest pain points in neuroscience research? Is it just the data, or is there more?
So neuroscience is, because it's evolving very quickly, it's the least standardized field of any so we're studying the most complex systems, but often we scientists are scrappy. They sometimes we use the word, very often, too often we use the word heroic effort, where you start from scratch with basic tools and then build up and then accumulate. And with the blood, sweat, and tears of graduate students and postdocs and investigators, build systems from scratch. It takes an enormous amount of effort, building the hardware, the software, the systems, all the synchronizations. It works. It's very fragile. And for someone to reproduce that, it becomes very... other fields have already gone through that process of standardization and a bit of automation, and neuroscience is behind in that, and for good reasons, because it's more complex, more very quickly evolving now. So things like genomics, fields like genomics, they have already gone through that standardization process, thanks to the Human Genome Project and a lot of other, and a lot of industry partners have built tools. So if you buy a system, it comes with it all its data management, and that has not yet happened as much as in neuroscience. And so in neuroscience right now, it's a bit non-transparent. Even so, typical lab, the principal investigator will supervise several students. The principal investigator is typically very busy writing grants, presenting. The students analyze the data. Even the principal investigator has doesn't have the time, the ability. It's very opaque to them. They see the final results. And in the few cases of scientific misconduct, fraud in neuroscience have been publicized recently. And in many cases, it was due to the inability of the investigator who's in charge of the project to be able to verify, to lift every rock to see what actually happened. And sometimes it takes years before the next generation of postdocs or graduate students cannot reproduce the data. It takes them years to figure it out. And so that level of complexity that scientists have to build with that opacity, and that leads to unreliable results.
Yeah, I think it is a particular challenge in something that's as complex as neuroscience. You have the biology side of it and what you're trying to accomplish and learn, right? But then you also have the technology side where, a lot of these, PhDs, et cetera, they're not necessarily computer programmers or understand how to structure a program. I know I was involved in some during the human genome days of, some great research that was done by a doctor, a PhD researcher, data scientist, but the tool wasn't really structured in a way that would allow it, for example, to run for days without it crashing and things like this, right? And so we get involved to try to help that. But the research, of course, is what has to come first, and then how do you actually implement it? So that's interesting. And then the brain just has, I think I was reading, preparing for this, just a massive amount of data, right? Just massive. I don't know what the number is, but it's if a little millimeter is huge, but I can't imagine what the whole brain has in it.
That cubic millimeter, and I'll make a controversial statement that someone will argue with. That cubic millimeter, part of the Microns project, which will be published in Nature as a special issue next month. Okay. The amount of data of just electron microscopy from that cubic millimeter is about a petabyte. Of just the controversial statement is that this is probably the most studied piece of tissue ever done in science. So on that scale, with that resolution, a millimeter does not sound like a lot, but in the brain, a lot of things happen at that scale.
So how do we take that and apply machine learning?
The stated objective of Microns was to design less artificial intelligence that's a little bit closer to biological intelligence. And that was the stated purpose. But for the study itself, a lot of machine learning was used. So as one of the investigators on the project, Sebastian Sunk, said, ask not what neuroscience will do for AI, we ask what AI will do for neuroscience. and I like that. I like him because what ended up is what we're learning a lot about the brain, but we apply a lot of methods to study the brain right now. I would say the benefit is still more from machine learning to neuroscience than from neuroscience to machine learning. And so in this particular project, machine learning was used throughout. So to analyze, so for example, to even segment the data, to translate just the grayscale cube of grayscale data into connectivity and cytoarchitecture, that took a lot of new machine learning, where it was at Princeton lab, Sebastian Sung's lab in Princeton, where at first they had graduate students manually follow axons and dendrites, and then they trained algorithms to do that. And one of the biggest impediments to everything, so algorithms work well when the data is super good. Algorithms fail when quality has any kink in it, and this is where humans have to resolve it. So it took an enormous amount of effort of supervised, human-based input that was then used to retrain machine learning algorithms. But to make sense of, we're entering this era where making sense of data is no longer possible by looking at it or even running statistical tests. You really have to run machine learning algorithms to detect anomalies in the data, unexpected things, and also to learn patterns from the data. So,
because it's such a massive data set, and then also the interconnections and everything, one person can't literally get their head around it, right? You need to use AI to really help.
Yeah, AI, machine learning is part of AI, and that spans a lot more. It spans multiple, but also combining physical methods and yeah.
So you said they were, at first, one of the goals of the project was to try to like recreate the human brain, for example.
Mm-hmm.
And how far away are we from that with these large language models that are essentially using something very similar to like training neurons, et cetera, right? And I don't know how many data points they're at, but in comparison, like to the human brain, is that something?
Yes. So we're getting to the point where the number of so first of all, I will say this, and again, it will be controversial that we overestimate how close it is to the connection between artificial neural networks and the brain. The brain remains a mystery. How the brain learns is, so algorithms that we now apply for like transformers or backpropagation, these algorithms that are used, they're fundamental to machine learning and resulted in some Nobel Prizes, and they're not a feasible representation of what happens in the brain. The brain functions very differently. The moment you look at it, the activity, it's much more generative in the sense that it's the way algorithms learn is very passive. They just machine learning algorithms right now are designed. They just sit there and they pass through immense amounts of information. And learning in humans and in animals is not possible without interaction. It's more generative. So all circuits they generate spontaneous activity in the brain. And that spontaneous activity is very fundamental to learning. Whereas all the machine learning algorithms, all the AI right now, it's more driven by input. Even ChatGPT, it responds to your input. But
it's not generating anything on its own. It's called
generative.
Right?
So the word generative isn't there,
but not generative.
Yeah. So it doesn't. And if you take a mouse from birth or a kitten, and freeze them, not freeze, sorry, keep them in place, and just play trillions of bytes of information, they will not learn from that. They learn fundamentally by interacting. The benefit of that is that animals learn from very few trials. They learn to interact. They don't need petabytes of information to learn something, new concepts. It can be like single trial learning. I have a kid. I know how, the first time he saw a lizard, it took him just a little bit to figure out why they're different from crocodiles, or, it didn't take me showing millions of pictures of lizards. I think we will learn to live in harmony with artificial intelligence, and in benefit. I'm very optimistic about that. But we will not be merging.
Okay. Well, I know some companies are trying to work on that too, right? So we're going to become the Borg at some point.
As maybe. A neuroscientist, I'm skeptical.
You're skeptical?
Yeah, yes.
Okay. Well, yeah, it's not a good look, probably.
At SoftTech, we don't just follow the trends, we set them. As the founder and CEO, I've built a team that excels in delivering cutting-edge solutions in software, hardware, and IoT. From concept to completion, we're the partner that turns your tech dreams into reality. SoftTech, where innovation starts.
So if I was a business and I'm looking at, how do I apply AI and I want to start organizing my data, any insights, in general, maybe outside of even neuroscience, but in a general way, any recommendations if you're a startup?
There are many different ways right now. One, there's a temptation, I think, that people are getting away from now with some discipline. There was a line of thinking maybe a couple of years ago, even some people think that now, that you can just pile the data and just collect it, make sure it's collected, and then unleash AI in it. And deception there is that AI may pretend, it may give you an impression of making sense of the data. If with a lot of work you cannot make sense of the data, the AI will not be able to make sense of the data either. You need to have a system, organizations, principles, the same principles. So fundamentally, DataJoint is based on a very rigorous approach that was developed over the past 2 centuries called relational theory, which is the foundation for relational databases. Relational theory is based on predicate logic from the 19th and set theory from the late 19th century, early 20th century, then was transformed into the concept of relational. Those principles are used in business. So your airline tickets, your banking is very based on very solid like data integrity, data consistency, those types of principles. In science, typically this has not been done in a lot of, so it's a lot more playing loose with a lot of things for good reasons.
I'm surprised by that, but continue.
Yes, for good reasons, because data is complex, evolving. You don't want to constrain yourself with structure and integrity and all those things. You're surprised. Why are you surprised?
Well, I would have thought that, especially with medical, that data and data integrity and quality data would just be like the norm.
This is, and I think this is the general expectation from the public. People expect, general public expects that in a scientific study, there's a rigorous data science or data operations, data integrity process.
Right.
Maybe on the medical clinical side of things, that's enforced and regulated. In the lab, generally scientists want to get to results quickly. They're very intuitive about it. They want to have that freedom to try new things, not be constrained by process and constraints. And they may intuit something, and then when they publish, they kind of put it together to make sure that the process, and that's where a lot of flaws. That's why the reproducibility crisis. If you follow it stems from that.
So that's where they've like, hey, we've created cold fusion, and it ran for 3 seconds or whatever, and then you publish the paper, and the other institutions go, that's interesting. I'm going to try to recreate this. And you're like, it's not working. I'm following the directions and nothing. It's not, I can't get it to go. Right.
Yeah.
So they kind of depend on that, kind of the validation from, say, multiple sources once they've published.
Yeah. So once you publish, this is the famous replicability crisis. Very few papers the result is reproduced. A significant fraction. If you do the same thing again, you will not come to the same conclusion. And even though if you follow the logic that's presented in the paper, it seems correct. Sometimes it's self-deception. Sometimes it's not. You got a data set and you tried 1,000 different methods and one worked, and it's like, yeah, that's meaningful, and you can publish. The process is very biased toward positive findings as opposed to disproving negative findings. So
no one's working on trying to disprove other people's findings, right?
Well, that's the first thing you need to be doing as a scientist. Yeah, but there is a publishing bias against negative results, and so you will not get tenure. And
I suppose I could see that where there's just so many things that we've learned and come up with that have been by accident in the lab.
That's right.
I mean, so it's not like you thought of something and you followed a certain process, and it's like you were doing something else and something else happened, and you're like, wow, that's interesting. Oh, I can actually store a charge in a jar or whatever, right? Or I don't know if that was an accident, but that kind of thing.
Yeah.
Right? So I can.
So I think the opportunity with AI is exactly this: to have computer systems that have the ability to say, oh, that's interesting.
So what's next for DataJoint, Dimitri? I mean, and how will it reshape neuroscience? We're not going to become the Borg, apparently, but what is going to happen?
We're not going to become the Borg. I think I'm very optimistic about the future. So a lot of activity now is around NeuroAI in the sense of studying intelligence, principles of intelligence generally. And this is where we're very well positioned. So generally across living systems and AI, I think when we call AI neural networks, it's a metaphor. Similarities end very quickly. And so we're still, there's a lot more to discover. So we're building technology that allows, it's not neuroscience specific, it's discipline agnostic for complex multimodal data. And we're just learning how to build AI into the discovery process itself, into this closed loop of induction and deduction, where you go from data to thinking about the hypothesis about the brain, integrating all the knowledge. So DataJoint now is focusing on first building that substrate for reliable data, but then building artificial intelligence on top of that to steer the scientific process. The scientific process is still running the same way it was during Faraday's time. Just the way we think, how when in my PhD, it took me 6.5 years, almost 6.5 years. You do a bunch of experiments for 6 months, then you go to your committee, and then you present, and then decisions are made about how all of that can now once permeated with artificial intelligence, just a year ago, everybody was skeptical that AI would play a significant role. In the last year, seeing the ability to form thoughts and chains of reasoning, I think is convincing most people who have looked deeply into it that it can be a tool to augment the scientific process.
And really accelerate.
It really accelerates. So closing the discovery loop. So that's what we call it. Closing the discovery loop. It's a caricature again, how science is done. But closing the discovery loop means to have technological augmentation at every step of discovery, going from in the literature review, finding gaps in the studies. And so as we look at each step, we see that right now, each step kind of requires a different approach, and coming up with a more unified model is a challenge. And so this is where we're partnering with other companies, with a lot of research labs, but also with funding agencies and foundations to really speed up that process.
Well, that's exciting. Well, we'll definitely post a link to that Nature episode. I think that'll be very interesting to watch. And thank you for coming on and talking about everything we're doing with the brain. I've got some computer socks for you.
Thank you.
To use your own gray matter with.
But, go with my brain socks. So this is
Thanks for coming on the show.
Thanks, Chris. Yeah.
I know how important staying informed is for innovation and growth. The Forging the Future newsletter brings you the best in tech trends, startup advice, and industry insights. Join our community and forge your future with us. Subscribe now.